1967. The damp English countryside. Within the sprawling landscape of the Mullard Radio Astronomy Observatory, a place of quiet scientific endeavor, an instrument known as the Interplanetary Scintillation Array meticulously mapped the radio sky. Its output, a continuous stream of squiggly lines on a chart recorder, was largely the domain of a young graduate student from Cambridge University, Jocelyn Bell Burnell. Day after day, she sifted through what many considered mere background noise, the cosmic static of a vast and indifferent universe. But then, a subtle, almost imperceptible anomaly appeared. A tiny piece of scruff, as she called it, a recurring blip that refused to be dismissed as interference. What Bell Burnell had stumbled upon was a radio signal, pulsing with a rhythm so incredibly precise it defied every known natural explanation. Every 1.337 seconds, like an impossibly perfect metronome, the signal arrived. This unwavering regularity, more accurate than any human-made clock, immediately presented a profound puzzle. Terrestrial sources were quickly ruled out. The signal's point-like origin clearly marked it as coming from beyond our world, a distant point in the cosmos. Her supervisor, Anthony Hewish, initially leaned towards the simplest explanation: faulty equipment, perhaps some obscure form of man-made interference. But Bell's meticulous observations, her unwavering insistence that this was something truly extraordinary, kept the anomaly on the team's radar. The scientific climate of the 1960s provides vital context for what happened next. Humanity had just begun its tentative reach into space, and the search for extraterrestrial intelligence, once the stuff of pulp science fiction, was beginning to evolve into a legitimate, albeit nascent, scientific field. Against this backdrop, the Cambridge team, half jokingly, half in genuine bewilderment, began referring to their mysterious signal as LGM-1, short for Little Green Men Number 1. The very idea of an alien intelligence beaming signals across the void was both thrilling and terrifying. It was a hypothesis that underscored the profound unknown they faced, yet also one that filled them with a very human fear: the fear of ridicule. The team worked under a veil of intense secrecy, debating internally what this signal could possibly be, wary of announcing a discovery that could be instantly dismissed as scientific delusion. This initial, incorrect hypothesis was a powerful testament to the human mind's innate desire to find patterns, to seek agency in the unknown, even when confronted with a phenomenon utterly unprecedented. How else could one interpret a signal of such unwavering, artificial-seeming precision? For months, the team grappled with the implications of LGM-1, running through every conceivable earthly explanation. But the universe, in its boundless capacity for the bizarre, was not yet done with its revelations. The crucial turning point, the moment that shattered the fantastical alien hypothesis, came with Jocelyn Bell Burnell's relentless dedication. She continued to monitor the skies, and her persistence was rewarded. 3 more similar signals, pulsing with the same astonishing regularity, emerged from completely different parts of the sky. This discovery of multiple, identical cosmic beacons from disparate locations was the definitive blow to the Little Green Men theory. The sheer statistical improbability of 4 separate alien civilizations, all choosing to broadcast precisely the same signal with the same inexplicable timing, was astronomical. The puzzle, once potentially a biological discovery, instantly transformed into a profound astrophysical mystery. The implications were staggering. If not intelligent life, then what kind of dead or dying star, what extreme physical process could possibly create such a perfectly timed, sweeping lighthouse beam in the heavens? This profound shift in understanding sets the stage for our entire exploration into the strange and wonderful. It reveals how the universe constantly presents us with data that we first attempt to interpret through the narrow lens of our expectations, before the relentless pursuit of science slowly, painstakingly, peels back the layers to unveil a reality far stranger and far more astonishing than we could have ever imagined. The cosmic ballet, often elegant and predictable, sometimes concludes with an act of unimaginable violence. When a star, many times more massive than our Sun, exhausts its nuclear fuel, it cannot sustain the outward pressure that counters its own immense gravity. What follows is not merely a stellar death, but a catastrophic implosion, a supernova. This cosmic explosion can momentarily outshine an entire galaxy, scattering the star's outer layers across vast interstellar distances. But it is what remains at the heart of this cataclysm that truly defies belief. A neutron star, the densest object in the universe known to science, short of a black hole. This isn't merely dense, it is incomprehensibly compact. Consider this: a typical neutron star, born from such a stellar demise, might contain 1.5 times the mass of our Sun, squeezed into a sphere only about 20 kilometers across. That's the equivalent of packing a mountain of material, far heavier than our Sun, into a city the size of London. To truly grasp this extreme state of matter, take a single teaspoon of neutron star material. That tiny amount, no bigger than your fingertip, would weigh billions of tons here on Earth, heavier than every single car and truck on the planet combined. It is a state where atoms themselves have been crushed out of existence, their electrons forced into their nuclei, combining with protons to form a sea of neutrons. But the most astonishing feature of these stellar remnants is not just their density, it is their incredible rotation. Think of an ice skater spinning gracefully on the rink. As they pull their arms inward, their rotation speed dramatically increases. This is a fundamental principle of physics known as the conservation of angular momentum. A dying star, before its collapse, rotates relatively slowly, perhaps once every few weeks or months. As it collapses into a neutron star, its colossal mass is concentrated into an impossibly small volume, pulling its arms of matter inward. This action amplifies its rotation to dizzying speeds, often hundreds of revolutions every single second. These are cosmic gyroscopes, spinning faster than any machine we could ever conceive. In 1968, just a year after Jocelyn Bell Burnell detected her perplexing little green men signal, two brilliant astrophysicists, working independently, unveiled the true nature of these cosmic beacons. The Austrian-born American Thomas Gold and the Italian Franco Pacini proposed what became known as the Lighthouse model. Their theory illuminated the strange, precise pulses astronomers were observing. They posited that a neutron star possesses an incredibly powerful magnetic field, 1 trillion times stronger than Earth's. This immense magnetic power channels beams of radiation shooting out from the star's magnetic poles like cosmic searchlights. As the neutron star spins at its astonishing rate, these two powerful beams sweep across the cosmos. If one of these beams happens to pass directly across Earth, much like the beam from a terrestrial lighthouse sweeps past a ship at sea, our radio telescopes detect a brief, intense pulse of radiation. The unwavering regularity of these pulses, once thought to be the work of intelligent aliens, was suddenly understood as a direct consequence of the neutron star's consistent, rapid rotation. This elegant model not only explained the mystery, but also transformed our understanding of dead stars. Confirming this model and discovering a veritable zoo of different pulsar types required a monumental leap in astronomical technology. The development of immense radio telescopes, like the iconic Arecibo Observatory in Puerto Rico, with its 305-meter dish nestled in a natural sinkhole, became absolutely essential. These colossal instruments, acting as giant ears, allowed astronomers to listen across vast stretches of the universe, picking up the faint, rhythmic ticks of these cosmic clocks. Through decades of observation, scientists have cataloged thousands of pulsars, each a unique testament to the extreme physics at play, and the applications of these cosmic clocks are nothing short of astounding. Perhaps their most profound contribution came in 1974, when two American astronomers, Joseph Houghton Taylor Jr. and Russell Hulse, discovered a binary pulsar system, two neutron stars orbiting each other. By meticulously timing the pulses from one of these stars over years, they noticed something extraordinary. The orbit was slowly shrinking. This subtle decay was exactly what Albert Einstein's theory of general relativity predicted if the system was radiating gravitational waves, ripples in the fabric of space-time itself. In 1993, Taylor and Hulse were awarded the Nobel Prize in Physics for this groundbreaking discovery, providing the first indirect evidence for the existence of gravitational waves, decades before instruments like LIGO could directly detect them. The pulsar, once a source of perplexing signals hinting at extraterrestrial intelligence, was revealed not as a message from another civilization, but as a far more profound testament to the universe's own extreme, yet entirely predictable, laws of physics. It is a cosmic lighthouse, not guiding ships to shore, but illuminating the most violent deaths and the most fundamental forces that shape our reality. The universe is a realm of extremes. We have journeyed through the compact, the impossibly dense remnants of collapsed stars that tick with unwavering precision. But now, we must shift our gaze from the precise cosmic clockwork to a phenomenon so vast, so overwhelmingly powerful, it can dwarf the light of entire galaxies. This is not some subtle whisper from the void, but a cosmic roar, a beacon that can outshine hundreds of billions of stars, yet it is a beacon born not of unique creation, but of a terrifying twist of perspective. Consider for a moment the very heart of a distant galaxy, countless light-years away. Buried within its core, we find the true engine of this cosmic spectacle, a supermassive black hole. These are not the stellar mass black holes born from individual supernovae, but titans of gravity, ranging from millions to even billions of times the mass of our own sun. If our sun were to be replaced by such a black hole, its gravitational pull would extend far beyond the orbit of Pluto, swallowing everything in its path. Around these gargantuan singularities swirls an immense maelstrom of superheated gas and dust, a cosmic whirlpool known as an accretion disk. The friction and gravitational forces within this disk are so immense that the material glows with an intensity that defies comprehension, releasing more energy than the combined output of all the stars in a typical galaxy. It is from this swirling vortex, this cosmic crucible, that something even more extraordinary erupts. The black hole's immense gravitational pull, coupled with powerful magnetic fields, acts as a cosmic funnel. These fields channel some of the superheated material from the inner edges of the accretion disk, accelerating it to velocities very nearly the speed of light. What emerges are colossal, twin relativistic jets, fiery spears of pure energy and matter, shooting out from the black hole's poles, perpendicular to the plane of the accretion disk. These jets, often stretching for millions of light-years across intergalactic space, are among the most energetic phenomena in the known universe. The crucial insight that unlocked the mystery of these powerful cosmic emitters came in the 1970s, spearheaded by brilliant theorists such as Martin Rees and Roger Blandford. They proposed that what we observe and how we classify these objects depends entirely on our line of sight, on our specific vantage point across the vast expanse of the cosmos. If we happen to view such a system from the side, with the jets stretching horizontally across our vision, we observe what astronomers call a radio galaxy, its radio emissions dominated by these powerful outflows. If our perspective allows us to peer directly down into the bright, swirling accretion disk, with the jets angled away from us, we classify it as a quasar, a quasi-stellar object, so luminous it can appear like a star despite being an entire galaxy away. But then there is the blazar. A blazar is not a fundamentally new type of cosmic entity. Instead, it is the same powerful beast, the active galactic nucleus with its supermassive black hole, accretion disk, and colossal jets, but seen from a very specific, and indeed terrifying, angle. A blazar is what we observe when one of those twin relativistic jets is aimed almost directly at Earth, like staring down the barrel of a galaxy's gun. This precise alignment triggers a phenomenon known as relativistic beaming. The light and radiation from the jet, already traveling at extreme speeds, are effectively beamed forward, dramatically amplified in our direction. It is akin to focusing all the light from a giant floodlight into a narrow laser beam pointed straight at you. The intensity from your perspective becomes staggering, making the blazar appear hundreds or even thousands of times brighter than it would if viewed from a different angle. This simple geometric orientation creates some of the most bizarre and initially baffling observational effects in astronomy. One such phenomenon which perplexed scientists for years is the illusion of superluminal motion. When astronomers observed blobs of plasma within these jets, they appeared to be moving faster than the speed of light, a seemingly impossible feat that defied the very laws of physics. It was a cosmic parlor trick, a mind-bending anomaly that challenged everything we thought we knew about the universe. The solution, however, lay not in breaking the cosmic speed limit, but in the subtle, profound physics of Albert Einstein's special relativity. The universe, it turns out, is a master of illusion, especially when its most powerful engines are pointed directly at us. The cosmic gun barrel we explored previously, aimed directly at Earth, reveals its terrifying power not always in the light we expect. Indeed, for the longest time, humanity remained largely blind to the true ferocity of blazars, those galactic engines whose jets pierce the void. Our telescopes, marvels of engineering though they were, captured only glimpses, the radio whispers, the optical glare. But the universe, in its boundless complexity, holds its deepest secrets in wavelengths that defy our natural vision. To truly comprehend these cosmic canons, to understand why they can appear to violate the very speed limit of light, required a radical leap in our observational prowess, learning to see the universe in the most energetic form of light, gamma rays. For centuries, astronomers had peered through optical telescopes, then listened with radio dishes, expanding our senses beyond mere eyesight. Yet, a vast spectrum of the universe remained a mystery, a realm of extreme energies that our atmosphere relentlessly blocks. The Earth's protective blanket, vital for life, acts as an opaque shield against gamma rays, the highest energy form of light, thousands to millions of times more energetic than the visible light that illuminates our world. This presented an insurmountable challenge for ground-based observatories. The solution was as ambitious as it was essential: take the telescopes to space. It was a high-stakes endeavor, launching instruments designed to capture photons born in the most violent corners of the cosmos, photons that could never reach us otherwise. A pivotal moment in this new era of cosmic exploration arrived in 1991 with the launch of NASA's Compton Gamma Ray Observatory, or CGRO. This groundbreaking satellite was a technological marvel, an orbiting eye designed to survey the entire sky in gamma rays, revealing a universe utterly unlike the one seen through traditional lenses. Then, in 2008, its successor, the Fermi Gamma Ray Space Telescope, took up the mantle, offering even greater sensitivity and a broader view of this high-energy realm. What these revolutionary instruments uncovered was a stunning truth, a cosmic revelation that remapped our understanding of the universe's most powerful sources. The gamma-ray sky is not dominated by nearby stars or familiar galaxies. Instead, it is a glittering tapestry of distant blazars, spread across billions of light-years, each one a cosmic lighthouse blasting immense energy directly at us. These gamma-ray observations were not merely pretty pictures. They were the missing pieces of a complex puzzle. They allowed scientists to finally connect the abstract theory of relativistic beaming, the idea that a Blazars jet, aimed at Earth, appears dramatically amplified, to concrete observational data. The sheer gamma-ray brightness and, crucially, the rapid variability of these sources perfectly matched the predictions of the jet pointed at us model. It wasn't just a theory anymore. It was now visibly, demonstrably confirmed by the most energetic light the universe has to offer. The observations from Compton and Fermi provided irrefutable proof that we were indeed staring down the barrel of a galaxy's gun, directly into the heart of its relativistic jet. But how do these jets produce such phenomenal amounts of high-energy photons? The answer lies in the extreme physics at play within them. One primary process is known as synchrotron radiation. Imagine a stream of electrons, particles with a negative electric charge, racing through space at velocities close to the speed of light. Now, place these electrons within the incredibly powerful magnetic fields that permeate the Blazars jet. As these superfast electrons spiral around the magnetic field lines, they are forced to emit energy, a kind of cosmic screech. This emitted energy manifests as photons, and given the extreme speeds and magnetic field strengths, these photons are born with immense energy, often in the form of gamma rays. Another critical process is inverse Compton scattering. This is where low-energy photons, perhaps from the accretion disk or even from surrounding starlight, collide with those same incredibly fast-moving electrons in the jet. Think of it like a game of cosmic billiards. A slow, low-energy photon is the billiard ball, and a super-energetic electron is the cue ball. When the electron slams into the photon, it kicks it, imparting a huge amount of its kinetic energy to the photon. This kick transforms the low-energy photon into a far more energetic gamma-ray photon, boosting its energy dramatically. These two processes, synchrotron radiation and inverse Compton scattering, act as the engines that power the Blazars' incredible gamma-ray luminosity, making them the most luminous objects in the universe when their jets are aligned with our line of sight. This deeper understanding of Blazars also shed new light on one of their most baffling characteristics, the illusion of superluminal motion. For years, astronomers observed blobs of plasma within these jets appearing to move faster than the speed of light, a seemingly impossible feat that defied Einstein's theory of special relativity. But the universe, it turns out, is a master of perspective. This illusion is not about breaking the cosmic speed limit, but about light travel time. Consider a powerful spotlight located far away, moving almost directly towards you, but also slightly across your field of vision. The light from the spotlight when it was further away takes longer to reach your eyes than the light from the spotlight when it's closer. Because the object is moving towards you at nearly the speed of light, the light pulses it emits are effectively catching up to each other, arriving at your telescope in a compressed time frame. This compression makes it appear as though the object covered a huge transverse distance in an impossibly short amount of time, giving the illusion of faster-than-light speed, even though it never actually surpasses the universal speed limit. It is a cosmic parlor trick, a demonstration of how deeply our perception of reality is tied to our vantage point in space-time. The journey through the gamma-ray sky stands as a profound case study in multi-messenger astronomy, a testament to how crucial new technological windows on the universe are for solving long-standing puzzles and confirming our most extreme theories. Without the ability to detect these invisible high-energy photons, the true nature and immense power of blazars might have remained forever shrouded in mystery. It highlights that the universe's most mind-bending phenomena often reveal themselves only when we are willing to build the tools to see beyond the familiar. Our previous journey plunged us into the ferociously energetic heart of Blazars, those cosmic cannons whose immense power redefined our understanding of light and motion. But the universe is a realm of infinite surprises, not all of them born of cataclysmic violence. Sometimes, the most profound enigmas arrive cloaked in an unsettling, almost serene beauty. Consider a celestial object so perfectly formed, so geometrically precise, yet so utterly alien to our standard cosmic classifications, that it seems to defy the very rules of galactic existence. This is Hoag's object, a galaxy that, by all conventional wisdom, should not exist. It was in 1950 when American astronomer Arthur Hoag first peered through his telescope and discovered this baffling entity. What he saw was unlike anything catalogued before: a stunning, near-perfectly circular ring of brilliant blue, young, hot stars. This stellar ring encircled a distinctly separate, much older yellow core, composed of ancient red stars. Crucially, between these two distinct components lay a vast, almost completely empty gap, a cosmic void separating the vibrant youth from the ancient heart. The sheer visual oddity of this object immediately challenged the established wisdom of galaxy morphology, a field largely dominated by Edwin Hubble's famous tuning fork diagram, which neatly categorizes galaxies into spirals, ellipticals, and irregulars. Hoag's object fit none of these. Arthur Hoag, grappling with such an unusual formation, initially posited a truly spectacular explanation. Perhaps he was witnessing a cosmic mirage, a phenomenon known as gravitational lensing. This effect, predicted by Albert Einstein's theory of general relativity, occurs when a massive foreground object bends the light from a distant background object, potentially creating a distorted image, even a perfect Einstein ring. It was a tantalizing hypothesis, suggesting a hidden, massive galaxy perfectly aligned to warp the light from something far behind it into this stunning ring. However, this idea was swiftly ruled out. Meticulous observations revealed that both the central core and the surrounding blue ring shared the exact same redshift, a measure of how much their light has been stretched by the expansion of the universe. This consistent redshift was conclusive proof. The core and the ring were at the same distance from us, some 600 million light-years away, and were, in fact, physically associated components of a single, bizarre galaxy. With gravitational lensing debunked, the central mystery deepened. How could such an improbable structure form in the first place? And more astonishingly, how could it remain stable for billions of years? The stark contrast between its two primary components is what truly defines the puzzle. The outer blue ring is a vibrant nursery of new star formation, teeming with massive, luminous stars that live fast and die young, indicative of recent, vigorous activity. Yet, the central core is a spheroidal galaxy composed almost entirely of ancient red stars, the kind typically found in an elliptical galaxy, a stellar population that has long since exhausted its gas and dust, the very raw material needed to form new stars or to create the flat disks and graceful spiral arms we see in more common galaxies. The profound, almost unnerving, lack of any visible connection between these two components is what pushes Hoag's object beyond mere curiosity into the realm of true cosmic anomalies. There are no faint spiral arms stretching from the core to feed the ring, no central bar-shaped structure guiding stellar populations, no delicate bridges of matter linking the two. It stands as a solitary, enigmatic structure, a cosmic fossil of a mysterious event that occurred unimaginable ages ago. This object effectively presents itself as a galactic crime scene, where the crime, the improbable formation of this ring, happened billions of years in the past. Astronomers, in turn, must assume the role of cosmic forensic scientists, meticulously piecing together clues from the faint light that has traveled for 600 million years across the vast emptiness of intergalactic space, searching for an explanation that fits this unparalleled defiance of galactic convention. What cosmic forces could sculpt a galaxy into a near-perfect ring, leaving an almost empty void at its heart? Hoag's object, that hauntingly serene enigma, stands as a profound challenge to our understanding of galactic evolution, a cosmic crime scene where the evidence is billions of years old. To solve this deep space mystery, astronomers have donned their detective hats, sifting through light that has traveled for 600 million years, piecing together competing theories about its improbable birth. The prime suspect in this galactic whodunit is a dramatic, catastrophic event, the collisional ring galaxy model. Picture a vast, sprawling disk galaxy, perhaps similar in scale to our own Milky Way, rich with the gas and dust that form the raw material for new stars. Now, visualize a much smaller, dense bullet galaxy, perhaps a compact elliptical, hurtling through the cosmic void. This theory posits that billions of years ago, this rogue bullet plunged directly through the very center of that larger, gas-rich disk galaxy. It was not a head-on collision that would obliterate both, but rather a clean, precise pierce. This incredibly rare, head-on impact would send a shockwave rippling outwards through the larger galaxy's interstellar gas and dust. Think of it much like the concentric circles that spread across the surface of a placid pond when a stone is dropped precisely into its middle. This galactic ripple, a ring-shaped density wave, would sweep through the disk, compressing the gas and dust it encountered. The sudden increase in density would act as a powerful trigger, igniting a furious burst of new star formation. This violent yet beautiful process would create the brilliant blue ring of hot young stars we observe in Hoag's object today. Meanwhile, the bullet galaxy, having completed its journey through the galactic heart, would have long since sped away into the cosmic distances, a phantom culprit vanishing from the scene of its billion-year-old crime. This model, championed by astronomers like Kenichi Wakamatsu, paints a vivid picture of cosmic violence leading to improbable beauty. Yet, this elegant solution carries a significant flaw, a glaring piece of missing evidence that keeps the case open, the complete absence of the culprit galaxy. If such a catastrophic impact truly occurred, where is the other galaxy? The immense gravitational interaction required to sculpt such a perfect, vast ring suggests the bullet galaxy should still be somewhere in the vicinity of Hoag's object, perhaps flung out to a distant but detectable orbit, or at least leaving a clearer trail of disruption. Its total disappearance from the observable vicinity remains a major challenge to the collisional ring model. This glaring absence leads us to a second major hypothesis, a far more gentle, almost serene alternative: the accretion model. This theory suggests that Hoag's object may have formed not from a violent impact, but from the slow, steady infall of pristine gas from the vast, diffuse intergalactic medium. This gas, over immense stretches of cosmic time, perhaps billions of years, would gradually drift towards a pre-existing stable galaxy. But not just any galaxy. This model proposes a central, already formed yellow core, perhaps a slightly elongated, bar-shaped galaxy, which could provide the gravitational scaffolding for the incoming material. As the gas slowly accreted, it would settle into a stable, ringing orbit around the central body, far from its existing stellar population. Over eons, this accumulated gas would gradually become dense enough to begin forming stars, creating the vibrant blue outer ring of Hoag's object. This accretion hypothesis neatly avoids the central problem of the collisional model. There is no missing culprit galaxy because there was no collision. The ring simply formed from the slow gathering of raw material. However, this gentler scenario struggles to explain two defining characteristics of Hoag's object: its almost perfect circular symmetry and the precisely empty gap separating the old core from the young ring. A slow accretion process might naturally lead to more irregular or diffuse structures, making the exquisite perfection of Hoag's object a formidable challenge for this hypothesis. So, how do scientists weigh these competing explanations for such an extraordinary cosmic formation? The answer lies in the relentless power of computational simulations. Astronomers do not merely theorize, they build virtual universes. Using supercomputers, they run thousands upon thousands of virtual galactic encounters, simulating every conceivable scenario. They model galaxies with different masses, speeds, angles of impact, and gas contents. They then observe how these virtual galaxies evolve over cosmic timescales, often tracing the development for billions of years in a matter of days or weeks on a computer. By meticulously comparing the results of these simulations, the resulting shapes, sizes, stellar populations, and empty spaces, to the precise observational data collected from Hoag's object, they can test which theoretical scenario best reproduces the observed structure. This is the crucial interplay between observational astronomy, which provides the precise cosmic data, and theoretical modeling, which offers the frameworks for understanding it. Each simulated collision, each accretion event, is a step closer to unlocking the ancient secrets of Hoag's object, a galactic ghost story waiting to be fully told. What if the most profound strangeness in the universe is not out there, but in here? What if the bizarre phenomena we uncover, the cosmic anomalies that baffle our greatest minds, are not merely physical entities, but something far more personal? A celestial Rorschach test, an inkblot onto which we project our deepest assumptions, our ingrained biases, and the inherent limits of our own understanding. This is the hidden thread that binds the rhythmic heartbeat of a pulsar, the blinding glare of a blazar, and the impossible ring of Hoag's object. These aren't just cosmic curiosities. They are mirrors reflecting the intricate workings of the human mind. Consider the very first encounter with a pulsar, that incredibly precise radio signal pulsing every 1.337 seconds. Why did Jocelyn Bell Burnell and her Cambridge team initially, even jokingly, label it "little green men"? It was not a sign of scientific negligence, but a direct consequence of how the human brain is hardwired. For millennia, on the primordial savanna, our survival depended on detecting patterns and inferring agency. A rustle in the grass, a regular drumbeat, our minds were primed to ask, who is doing that? What intelligence is behind this pattern? This cognitive bias, honed by evolution to keep us safe from predators and connect us to tribes, becomes a double-edged sword when interpreting the vast, indifferent cosmos. That unwavering regularity, far more precise than any known natural celestial phenomenon at the time, screamed artificial to minds conditioned to find design. It was a perfectly rational, yet utterly misleading, interpretation born from our very nature. Then reflect on the Blazar, a galactic engine whose relativistic jets create the illusion of superluminal motion, appearing to move faster than light itself. This cosmic parlor trick did not just baffle astronomers. It directly challenged our fundamental, pre-relativistic biases about space and time. Our everyday experience is rooted in a static, three-dimensional Euclidean space, where objects move linearly and clocks tick uniformly. When observing a plasma blob seemingly covering a vast transverse distance in less time than light could travel, it shatters this intuitive framework. The Blazar forces us to confront a profound, counterintuitive truth. Our very position in the universe, our specific line of sight, dramatically alters the physical reality we observe. It compels us to accept the profound implications of Albert Einstein's special relativity, where time and space are not absolute, but are intertwined and relative to the observer. Finally, turn to Hoag's object, that hauntingly serene ring galaxy, a bright blue halo of young stars encircling an ancient yellow core, separated by a seemingly empty void. Its very existence defies our neatly categorized models of galactic morphology. For decades, astronomers have relied on diagrams like Edwin Hubble's tuning fork, classifying galaxies into spirals, ellipticals, and irregulars. Hoag's object, with its impossible structure and the profound lack of any visible connection between its components, challenges this deeply ingrained bias towards assuming that common forms, like the graceful spirals or the stately ellipticals, are the only stable or even possible outcomes of galactic formation and evolution. It is a cosmic fossil, a structure that whispers of events and processes beyond our current understanding, forcing us to reevaluate the very rules we thought governed the universe's most massive structures. This deep dive into pulsars, blazars, and Hoag's object transcends mere astrophysics. It makes a powerful interdisciplinary leap, connecting the grand scale of the cosmos to the intricate workings of cognitive psychology and the philosophy of science. It argues that the strangeness we perceive in these objects is not an intrinsic property of the universe itself. The universe is simply what it is. Instead, this strangeness is a measure of the gap, the profound chasm between cosmic reality and our mental models of it. Each strange discovery, each anomaly that forces us to scratch our heads and rethink, is therefore not just a revelation about the universe's extreme physics or improbable structures. It is, perhaps more importantly, a revelation about the limitations and the boundless potential of the human mind itself. These cosmic inkblots force us to be more humble in our assumptions, more creative in our theorizing, and infinitely more rigorous in our relentless quest for knowledge. The universe, in its baffling beauty, constantly reminds us that the greatest journey of discovery often begins with questioning what we think we already know. Every journey, however profound, must eventually find its concluding chapter. Yet, the cosmos itself offers no such neat finality. We have ventured deep into the heart of cosmic strangeness, exploring objects that defied our initial understanding, from the precise, otherworldly beat of a pulsar, a misunderstood pulse that revealed the true nature of dead stars and exquisitely tested the very boundaries of Albert Einstein's general relativity, to the blinding, deceptive glare of a blazar, a trick of cosmic perspective that unveiled the raw, unfathomable power of galactic engines. Our path then led us to the hauntingly serene puzzle of Hoag's object, a ghostly ring of stars that relentlessly challenges our entire story of how galaxies are born and evolve. But here is the profound truth we have uncovered. Every truly strange object in the universe is not a problem to be simply solved and filed away. It is a gift. It is an anomaly, a cosmic outlier that forces us, the explorers, to refine, or sometimes even to outright discard, our most cherished and long-held theories about how the cosmos works. These celestial enigmas are not mere curiosities, they are signposts, pointing us toward a deeper and far more complex understanding of the universe than we could have ever imagined. This fundamental lesson now propels us forward, pushing the very limits of our technology. Consider the Vera C. Rubin Observatory, currently taking shape high in the arid expanse of the Chilean Andes. This revolutionary instrument is designed not just to observe, but to create a dynamic, living portrait of the universe. With its colossal mirror, nearly 8.4 meters across, and a 3.2 gigapixel camera, the equivalent of more than 2,000 high-definition television screens, it will survey the entire observable sky every few nights, building an unprecedented time-lapse movie of cosmic change. It will detect transient events, subtle shifts, and fleeting phenomena that have, until now, remained utterly invisible to us, revealing a universe far more active and unpredictable than previously thought. And stretching across two continents, Australia and South Africa, lies the distributed network of the Square Kilometre Array, or SKA. When fully operational, this will be the largest radio telescope ever built, boasting a collecting area equivalent to 1 million square meters, or over 100 football fields. Its unprecedented sensitivity will allow us to map the radio universe with a clarity and depth previously unimaginable, detecting whispers of energy from the very first stars and galaxies, and perhaps the faint signatures of objects we have yet to even conceive of. This immense array will allow us to probe the most distant and ancient reaches of the cosmos, listening for signals that have traveled for billions of years. With these colossal new eyes and ears on the cosmos, scientists anticipate that not just hundreds, but literally thousands, if not millions, of new strange objects will flood our astronomical databases. We are on the cusp of discovering pulsars in truly bizarre binary systems, perhaps even triple or quadruple star configurations, their intricate gravitational dance revealing new complexities in the fabric of space-time and providing even more precise tests of gravity. Blazars, too, will reveal unexpected properties, perhaps extreme variability that hints at entirely new physics near the supermassive black hole, or unique emission patterns that defy current explanations. And perhaps most excitingly, we are poised to uncover entire new classes of galactic structures, formations so utterly alien to our current classifications that they will make the serene enigma of Hoag's object appear almost mundane by comparison, pushing the boundaries of our galaxy formation theories even further. The universe, ultimately, is not strange in and of itself. It is merely indifferent to our expectations, to the neat categories we construct to make sense of its staggering immensity. The true adventure of science, the very heart of exploration, lies not in finding things that simply confirm what we already know, or in filling in the blanks on a familiar map. It resides in encountering the anomalies, in pursuing the outliers, and in deciphering the puzzles that stubbornly reside on the very edge of our celestial maps. These are the uncharted territories, the cosmic wilderness, where the next great revolutions in our understanding are patiently waiting to be found. For the ultimate strangeness, the true cosmic paradox, would be a universe that held no more surprises for us to uncover.